Howdy, everyone. Happy Thursday. Today is not St. Patrick's Day. Today is not Pi Day. Today is not the Ides of March. But just to make it different, we're going to pretend it's a Friday. So we can go ahead with lecture. Okay, last time where we stopped, we finally got around to talking about polyatomic molecules. Quick reminder, if you have anything other than a linear molecule, you're going to have 3n minus 6 vibrations. And the 6 comes from the fact that polyatomic molecules typically have 3 translations and 3 rotations. Diatomic molecules have only 2 rotations. So we started looking at water, and here are the experimental results for the 3 vibrations of water. And the thing I want to emphasize again, infrared absorption and vibrational spectra are different from NMR in that like bonds do not give just one single frequency. In NMR, if you have 2 equivalent hydrogen atoms, you get just one chemical shift. With vibrations, the 2 equivalent hydrogens here move together either symmetrically or anti-symmetrically, but you get 2 vibrations with different vibrational frequencies. Okay, so mathematically, if we wanted to solve the Schrodinger equation for this, and our nice big supercomputers now do this quite readily, you can figure out what all of the vibrational frequencies should be for a molecule. So these computer programs can figure out what the bond strengths are, and from those they calculate force constants, and then you can figure out what the vibrational spectra should look like. Okay, so let's look at what the potential function should look like for water. And in water, we have 2 equivalent OH bonds. We're labeling them R1 and R2, and there's an angle that can bend, alpha. So these are called internal coordinates, and if you look at the vibrations at the top of this page, those vibrations can be defined in terms of these coordinates. So the first vibration would be R1 plus R2. The 2 bonds are stretching at the same time. This anti-symmetric stretch would be an R1 minus R2. They're in opposite directions. And then this angle bending would just be defined by the coordinate alpha. So how should we write a potential function? We can start off pretending that parts of this molecule are just like diatomic molecules. So we have an OH stretch. We could write that as 1/2 kx squared, where x is the stretching of R1. But here, to make it clear, instead of writing x, let's write delta R1. And instead of writing 1/2 k x squared, I'm changing the k to a little f that stands for force constant. The subscript r means it's the force constant for a bond stretch here. And also, instead of writing a half on the right-hand side, I pulled a 2 to the left. That way I don't have to keep writing 1/2s all the time on the right-hand side. If you like that 1/2 on the right side, that's okay too, but I prefer to write 2v is equal to this. So hopefully to everybody, it's clear that if we had just a diatomic molecule OH here on the left, we could write its potential function as 2v is f sub r delta R1 squared. So that would be the diatomic model for that bond. Now we see that bond R2 is equivalent to R1, so it's going to have the same force constant, which we're calling f sub r. And so the next term will be delta R2 squared. Keep in mind that we're writing the potential energy for all of the vibrations of this molecule, all 3 vibrations. The third motion we can have is the bending of this angle, and we haven't talked about what kind of forces are present, but as a start, let's just say it's a quadratic dependence again, so it'd be like 1/2 f alpha delta alpha squared. So way back when, maybe in the 1940s or 1950s, before people had computers and calculations were very lengthy, This was the model that people try to put into the Schrodinger equation to figure out what the vibrational frequencies would be for water. And it did not do a very good job. And if you think about it, I think you'd see why. If we stretch R1, that's going to shift some electrons and bonding around in this bond on the left, and it's going to influence the bond on the right. So that means there's an interaction between R1 and R2. Both the bonds are connected to the oxygen, and so if one bond is stretching, the other is going to feel a difference in its own forces. So people soon discovered that there should be interaction constants, and so the interaction between R1 and R2 was simply written F sub RR, delta R1, delta R2. So that's just the nomenclature that was used. And people then also realized that a bond stretching could also affect how much force it takes to bend the angle alpha. And so we have an interaction, constant interaction term between R1 and alpha. So I put the deltas in there to indicate that this is how much displacement you have from their equilibrium position. So you remember in the harmonic oscillator, we had 1/2 kx squared. X0 was at the equilibrium point, but then if you went away from X, then that was a displacement from the equilibrium point. Okay, so both delta R1 and delta R2 can interact with delta alpha. So this is a definition of what you have to deal with if you want to do a so-called force constant calculation. And many people in the early days of computers, before they got so good that they could actually figure out what force constant should be, many of us, including my laboratory, would spend quite a lot of time collecting vibrational spectra. And then we would figure out what do the force constants have to be in a molecule to give us the spectra that we see. Now, notice here, we have a total of FR, F alpha, FRR, and FR alpha. So there are 4 force constants for the molecule. But when you collect the spectrum of water, you only see 3 frequencies. So you cannot determine from just the water spectrum what these force constants would be. So vibrational spectroscopists also go to isotopic species. As I mentioned before, D2O, the heavy isotope form of water, deuterium of mass 2, is readily purchasable. You can run the spectra of that, and you get 3 more frequencies, and they will be shifted because of the mass term effects that you're going to have here. I mentioned that this you can put into the Schrodinger equation, but I didn't also mention the fact that you also have to worry about how the mass terms, how the kinetic energy terms change. So if we do both of these isotopic forms, we're going to have 6 vibrational frequencies, and we only need to determine 4 constants. So that's pretty readily done to calculate the force constants of the water molecule. Okay, so what does the water spectrum actually look like? And I apologize, I can't turn these sideways with my current version of Adobe PDFs. So you have to tilt your head and look at it sideways. This is just a spectrum of air. And this is in an infrared spectrometer that we have. It's constantly being purged by dry nitrogen. So we're trying actually to get rid of all the water and all the carbon dioxide that's in the air. So right up here, you can't tell, but there's 2 vibrations of water, the symmetric stretch and the anti-symmetric stretch. Remember that we said these frequencies are 3652 and 3750. So they're kind of on top of each other. And what you're seeing is a lot of structure. And as you might guess, the structure comes from rotational contributions to these bands. We're not going to get to worrying about analyzing the rotational fine structure, but from that, you can also get the rotational constants of water if you wanted to do it. But there's also a P branch and an R branch, and you can see up here the Q branch is pretty much missing. In other words, delta J0 is not very strong, and so you're just seeing a lot of rotational fine structure here. The band here at about 1600, this is the angle bending of water. And again, you can see the rotational fine structure gap in the center. So this looks a lot like what you see for diatomic molecules. I also wanted to point out that we're seeing CO2 in air. The natural abundance nowadays of carbon dioxide in air is 0.04%. So that sounds very, very small. As you know, we all worry about global warming, and a lot of it comes from carbon dioxide. In fact, the two main culprits for global warming are water and carbon dioxide. Doesn't look like much in this spectrum, but when we go to the next one, you'll see it. Carbon dioxide, it's a linear molecule, so it has 3n minus 5 vibrations. That comes out to be 4 vibrations. One of them is the symmetric stretch, and so the molecule's going like this. That has no dipole moment change, so you can't see it in infrared. This vibration right here is the anti-symmetric stretch. One bond is getting weaker or shorter, the other is getting longer. It's going back and forth. And then up here at 676 is the bending vibration of CO2. It's a linear molecule, but it can bend one way down or the other sideways. So this is a pair of vibrations degenerate. So 2 here, 1 here, and 1 that we can't see that shows up in Raman spectra. Now, I do want to tell you a little bit more about global warming, and next week after we have our review for the exam, I'll show you some slides of from a global warming expert on what's really going on. But let me just first emphasize what atmospheric air looks like. So what I showed you up above was purged laboratory air trying to get all the CO2 and water out. The spectrum on the right is now a more normal spectrum of air, and you can see how much more intense these bands are. This has a path length of maybe 10 or 12 inches or something like that. So it's not a very much of a path length, but you can see the water absorbs close to 70–80% of the light in this region and that region, and CO2 right here and there absorbs maybe 50%. But what happens if you go look at atmospheric air? And I guess I don't have this here, but this may be through something like 50 meters of air, or perhaps not even that much. But what I want you to recognize is now the absorption by water and CO2 down in the bottom means that the infrared light at those frequencies cannot get through. And so the basis of global warming, as I'll show you in just a second, is that sunlight comes, hits the Earth, warms the Earth. The heat radiation coming off the Earth is infrared light. And when it hits CO2 and H2O in the air, in these regions where the curves go way down, the molecules in the air reabsorb it and re-emit it then in all directions. But about half of it immediately gets emitted back towards the Earth. And when you go through many layers of atmosphere, a great deal of the heat then is retained by the Earth. And it depends on what is the water vapor in the air, and then how much carbon dioxide there is. Okay, so I put this black and white picture in your notes. I'll show you a prettier picture of this. Back about 10 years ago, I was invited to give a talk at a math conference in Las Vegas about the mathematics of vibrations and things like that. And one of the other people there was an A&M professor in mathematics named Gordon Chen. And after the conference, the two of us were invited to write an article on the science of global warming, or the mathematics of global warming. And so that's basically what's shown on this cover here. This is a cover of that journal highlighting what we're going to talk about within the article. I'm having a hard time having it be fully on, but okay, you can get the basic idea of what's going on. All right, so here's the sun hitting the surface of the earth. People have calculated how many watts per square meter you get. And this is mostly, that most of the energy comes from ultraviolet light and visible light. Parts of it get reflected by the atmosphere, part of it gets absorbed by clouds, but there's a general sense of how much heat is hitting the earth. A lot of this visible and ultraviolet light then gets converted into infrared light, and you see here it's trying to come up. So we have water, carbon dioxide, some methane, there's the water. And when we have layers of that, then the spectra that I showed you on the page here, you can see a lot of that infrared light is going to be absorbed. And so when it's absorbed, some of it gets emitted back out towards space, but then it can get absorbed again by more CO2. But the gist of it is a large amount of it gets shipped back to Earth. Now, global warming, I should point out, is not all that bad. If we didn't have this occurring, the average temperature on Earth would be minus 15 degrees centigrade. As it is, it's plus 15 degrees centigrade, and we don't seem to mind that too much, except maybe in the summers in Texas to some degree. And now I'm going to look at a chat question. Somebody says, I think this man Jan might be Merlin. I'm not sure why I'm Merlin, but I can get an explanation later. Okay, so anyway, this is the gist of what is going on. Most of you, I think, know how greenhouses work. Maybe they're not so common in Texas, but up north, a lot of people have glass greenhouses. The glass transmits visible light and some ultraviolet light so the plants can grow. The light also warms up the interior of the glass greenhouse. And so that's infrared radiation, heat. So heat is infrared radiation. Glass mostly absorbs, or glass absorbs most of the infrared light. So very little infrared light or heat can get out through the glass just by direct transmittance. So you get a warmer greenhouse by that effect. And so this global warming effect is also called the greenhouse effect. Okay, so just wanted to show you that we were already, or many people were thinking about this more than 10 years ago. In fact, 20 years ago, people started getting concerned about global warming. So I stuck a few things into your notes. First, that page. Here's a measure of carbon dioxide levels over thousands and thousands of years done by glaciologists, a fellow named Lonnie Thompson at Ohio State University. He's also come to A&M and given the university lecture series talks and stuff. But I'll tell you about that next Friday, not tomorrow, but a week from Friday, about glaciology research and global warming and so on. The point of this is you probably can't read the numbers, but maybe you can in your notes. This is 300 parts per million carbon dioxide. We have now hit something like 405. And so we're having higher carbon dioxide levels than have been around for tens or hundreds of thousands of years. This is a little bit out of date. These are the latest CO2 measurements. We're at 415 parts per million. So that's a very small number. As I said, this is 0.0415% of the air is CO2, and it doesn't seem like it's very important. And CO2 only absorbs in a couple places in the spectrum. But when it does absorb, and if it increases global temperatures by a small amount, it also increases the temperature of our oceans. And when the temperatures of our ocean go up, then we're going to have more water vapor in the air. You get more water vapor in the air, it's also going to create more global warming. And again, that leads to more water vapor and more of the greenhouse effect taking place. I don't remember from what year this is. Okay, September 2019 that this was done. So these are warming projections that we've had. So in general, most people have thought that we've had something like I guess that's the case here, 1.3 degree centigrade global warming over the last century or so. But the projections for the year 2100, which hopefully many of you might be seeing, they can be pretty dire. And I've seen some predictions that temperatures could go up as much as 8 degrees centigrade. Baseline is kind of the curve that's estimated. If we don't change a lot of policies, we might be up 4 or 5 degrees. But I'll tell you more about that a week from Friday when I show lectures, show slides of glaciers melting and things like that. These aren't very good pictures, but just to give you an idea of what's going on. This is all ice in 1978. I think this is in Peru. Anyway, it's in the Andes. This is all a lake right now. This one is very hard to tell in black and white, but there was a glacier here, and you can see a lot of it's melted in this picture. Here's yet another one over the years. And so 1906 to 1994, you can see a lot of this is disappearing. So if anybody needs to have proof that we have a warming climate, you just need to look at these glaciers here. Okay, so let's go back now to look at vibrations of other polyatomic molecules. We've looked at water. I mentioned CO2. I didn't show you exactly what the vibrations were, but you had a symmetric stretch, an anti-symmetric stretch, and then the bending. Let's first take care of what larger linear molecules might look like. So let's take HCN. Linear molecule has 3n minus 5 vibrations. In this case, it's 4. So we can have a carbon-hydrogen stretch. It would be at 3304 wave numbers. Carbon-nitrogen triple bond stretch is at 2090. And then 2 vibrations occur exactly at the same value of 722. So you can bend this HCN angle either within the plane of the screen, or you can bend the molecule out of the screen. And both those vibrations would be the same. So you see we have 4 vibrations, but there are only 3 frequencies that you see. My notes are going to show the A1s and sigma pluses and pi's and stuff like that. That refers to symmetries. We're not going to cover that in this course. Someone says, I like our talk about global warming better. Okay. Infrared spectroscopy is the basis of global warming. So when we come back to this a week from Friday, I think you'll get a good view of what's happening to glaciers around the world, what the projections are. If things don't change, a lot of Florida is going to be underwater by the end of the century. Parts of Manhattan are going to be under water, and so we'll be looking at that too. Okay, question is the signal for the HCN stronger because of the degeneracy? Sure, if you have a degenerate vibration and you look at it, because there's two vibrations and two quantum states at the same value, that would double the intensity. I'm not showing you what the spectrum here is, I'm just giving you some frequencies. Okay, again, in this part, please ignore the symmetry aspects here, but I think I may have stuck into your notes some symmetry rules if you should get excited about it and want to read about it. But we don't have time in this course, since we have to talk about statistical mechanics also to talk about symmetry. But let's take a little bit larger molecule, and we'll take formaldehyde, 4 atoms. So 3n minus 6 leads us to 6 vibrations. When you apply symmetry, you can break the vibrational descriptions into 3 categories. The first group are the most symmetric, and then the later ones get to be less symmetric. But here I just want to give you an idea of what to expect for this molecule. If you look at the CH2 part here, you'll see this is a lot like water. So this is a lot like water. So you'd expect that you can have a symmetric stretch of the CH2 group, or you could have an anti-symmetric stretch. And over here on the right, I have pictures of those vibrations. So keep in mind that if I don't show you a dynamic model where the bonds are actually vibrating, I indicate it with vectors. So the first vibration just looks like this, where the 2 CH bonds are vibrating very fast, 10 to the 14th times per second. In wave numbers, the symmetric stretch comes out to be 2783, the anti-symmetric stretch 2843. So both bonds stretch here at the same time, back and forth. Anti-symmetric stretch, while one bond gets longer, the other gets weaker. The vibrations in each of these symmetry groups are typically labeled high to low. So this one's called nu1, nu2, nu3. So nu2 here winds up being the carbon-oxygen stretch. And as I mentioned last time, I believe, the carbon-oxygen double bond stretch in ketones or aldehydes, it's typically around 1700, 1750 wave numbers. Here it's at 1746. The third vibration that's highly symmetric is this angle bending. And you'll see this again looks very much like the angle bending in water. For formaldehyde, this occurs at 1500 wave numbers. I've already mentioned the anti-symmetric stretch for water, but there are 2 additional vibrations that involve bending of angles. So nu5 here is called a carbonyl in-plane wag. And if you picture this and think of formaldehyde being a dog, and this is a dog's tail, you see the tail just wagging back and forth. So you'd call this the wagging motion for CO. And these motions typically get to be a lot lower in frequency than bond stretching. So this is at 1249. And then the last vibration for formaldehyde is this CO out of plane vibration. And you can see, well, you can see if you can read it, I think this is 1167. This again drops in frequency. But note what we have in this molecule. We have 3 bonds, and we have 3 stretching vibrations. That's a pretty good rule of thumb. So if you have a molecule with 18 bonds, you can expect to have 18 bond stretching vibrations. But all of the other ones wind up being some kind of angle bendings or twists or wags or things like that. And so you can see in formaldehyde, this motion, which is also called a scissors motion, this wag and that wag, they do not involve bond stretches. Okay, again, I have some symmetry stuff. So we're going to look at this organic molecule here. And I like to show the spectra and discuss this molecule. I think it's already been something like 40 years ago. I was invited to write a chapter in a book comparing infrared and Raman spectroscopy. And I found this molecule to be an ideal example for showing you what kind of vibrations you have. So when I'm going to say some things first, but after I discuss it initially, uh, I'm going to show you the spectra, and I'm also going to show you dynamic models of these vibrations. But this is the infrared absorption spectrum. This is the Raman spectrum. And you can see they look totally different. You wouldn't think it's the same molecule when you're looking at it at all. But here's a case then where both infrared and Raman can help you understand the vibrations. So the vibrations are actually listed here. But first, a few comments. So when we go looking at the spectra, the strongest infrared absorption is going to be the one with the largest dipole moment change. So we have a carbonyl group. The carbon atom has a partial positive charge. The oxygen atom has a partial negative charge. So if you look at the spectrum, this is the carbon-oxygen stretching band, and you can see it's the strongest. When I go back to the previous page, I'm going to tell you one of the strongest Raman bands is the carbon-carbon double bond stretching. And this is the one labeled number 4. So you can see this is a very nice, strong band. In infrared, it's very, very weak because there's not much dipole moment change at all when you have this vibration. So here's the picture for the carbonyl stretching. So you remember I have said that if you see a change in the electron distribution, if you see a change in the shape of the vibration, here we have the carbon-carbon double bond at equilibrium. It shrinks down, gets a shorter bond, and then it stretches. At the two extremes, the molecule's polarizability is very different. Polarizability is the ability to drive electrons to one side of the molecule when you hit it with an intense light beam, like a laser. So these are two of the vibrations that we have. I'm going to stop the share, and then we'll go look at dynamic models of the vibrations of this molecule, if I can find them. I want to turn this on, but does anybody know the key to get it into the action mode of a PowerPoint? I may stop sharing it and activate it before we start. I'm still working on trying to get it to go. Okay, now I think we can do it. All right. Okay, so this is the molecule that we're talking about. What we have initially here, these are computed spectra for the molecule, but we're going to talk about that in the lecture notes, so I'll skip over those. There's a listing of the vibrations. And what I'm going to show you is what all the vibrations are of this particular molecule. These are generated by the computer, but in almost all cases, they're within 1 or 2% of the correct frequency that we have for the molecule. So obviously, I'm not going to expect you to memorize what these vibrations are, but what I'm hoping to show you is that you can get some appreciation for what the characteristics of the vibrations are. So we're going to start with the highest frequencies. These are the ones that are going to have the lowest reduced masses. So when we have a carbon-hydrogen stretch here, for example, the hydrogen is very light, the reduced mass is light, carbon-hydrogen bond is sufficiently strong, so this is the highest frequency that we have here. Whoops. Okay, that was the symmetric stretch. Now here's the anti-symmetric stretch. And you can see very little of the rest of the molecule is moving. One of the requirements for vibration is that the center of mass doesn't change. So you can see the carbon atoms are having to adjust a little bit when these hydrogens are moving. Okay, this one is now the CH2 stretch. So these CHs at the double bond are stronger bonds than these alkane type carbons. So this one, by the way, is called an anti-symmetric out-of-phase stretch. It's anti-symmetric because the one bond is stretching while the other is increasing. And if you compare the carbon on the left to the carbon on the right, they're out of phase with respect to each other. When this hydrogen is going in, the equivalent one on the other side is going out. Okay, this one now would be called an anti-symmetric stretch in phase. This is a symmetric stretch in phase. And you can see the frequencies are dropping. Anti-symmetric stretches are almost always higher in frequency than symmetric stretches. That just comes from the mass effects that you have when the vibrations take place. Okay, so this was the symmetric stretch out of phase. And I have a chat comment. Okay, someone says they want to have this on eCampus. I think we can do that. Okay, this is a little bit out of perspective, but this is the carbonyl stretching. It's all in the plane of the molecule, but the computer is trying to keep the molecule planar and making it vibrate. By the way, I should point out, and it's quite important to point out, we are greatly, very, very greatly exaggerating that amplitude of the vibration. Here it shows the oxygen smashing into the carbon, but a typical amplitude is only about 1/10 of the bond distance. So if this carbon-oxygen bond is something like 1.1 angstroms, then the amplitude is only going to be about 1/10 of an angstrom. And that was same as true for the carbon-hydrogen stretches. The bonds are about 1.08 angstroms, and they maybe vibrate 0.1 angstroms. Okay, here's the carbon-carbon double bond stretching. And I'm a little bit surprised nobody said, well, why is this infrared active, since we saw it in the infrared spectrum? Doesn't look like it has any dipole moment at all. Turns out that when this vibrates, the dipole moment change is actually in this direction, up and down rather than sideways. And that comes from the fact that we're forced to have some motion. As you can see, these CH2 groups are turning a little bit as these bonds vibrate. And so the dipole moment comes in that direction, and it winds up being really very small. Okay, vibrations like this are called deformations, CH2 deformation. More colloquially, many people like to call this a scissors motion. You can see it's just like a pair of scissors snipping away. This would be the scissors motion in phase for the vibrations. And then this would be the scissors motion out of phase, where the two groups are not closing and opening together with respect to each other. This one is a CH wag. As I mentioned, people like to call these wags when it kind of looks like a dog wagging its tail. Here I guess we have two dogs next to each other wagging their tails synchronously together. This one is now starting to get more complicated, and this is one of the harder aspects of vibrational spectroscopy. You can't always ascribe a single description to what's going on. This is mostly a CH2 wag in phase. So this group and the group up there, the CH2s are going sideways, just again like a dog wagging its tail. But you can see at the same time, there's a little bit of motion of these CHs right here. Okay, this one is then the CH2 wag out of phase. This side and that side are doing opposite things. This is called a CH2 twist. So at each carbon, you have these motions going back and forth sideways like this. We might not get to it today, but we will one day. I'm going to show you all the typical vibrations that an organic molecule like an alkane might have. And whenever you have a CH2 group, you're going to have a symmetric stretch, anti-symmetric stretch, a scissors motion, a wagging motion, a twisting motion, and a rocking motion that we haven't yet come up with. So all of these are known entities in typical organic molecules, and they make it easier to understand characteristics of some of the molecules people look at. Many chemical engineers wind up working with polymers. Polymers are typically made up of lots and lots of CH2 groups, and so it's kind of useful to be able to understand what an infrared spectrum shows. Here again is the CH wag. You can see this is where the two hydrogens are either moving apart or close together, rather than swinging to the left and right at the same time. We didn't exactly do a count of this molecule, but that's 3, 5, 7, 9, 11, 13 atoms. So we should have 39 minus 6, or 33 vibrations. So there's a lot of these. Here's another CH2 twist. This one is out of phase. This is now a CH2 rock. So this one is in phase. You can see why this looks like a rock. So picture grandma sitting here on this carbon atom. She's rocking in a rocking chair, and that's where the description comes from. This is a CH wag out of phase. Out of plane. So it doesn't really look like a dog wagging its tail anymore, but it's going in and out of the plane of this 5-membered ring molecule. Okay, it's kind of deceptive here. It looks like the hydrogens are doing a lot of motion, but this is a ring vibration. So notice this carbon-carbon bond gets weak, it gets shorter, while the one on the right gets longer. And you get a little bit of change in these carbon bond stretches here. This is mostly a carbon-carbon single bond stretch involving these two carbon atoms. Here's another CH2 rock. Here's another ring vibration. You can see here it's going pretty crazy. And a lot of the motion now involves this carbon-carbon bond and this carbon-carbon bond. You can see they go in opposite directions. Okay, let me give you a challenge. If you were to name this vibration, what would you call it? It's a ring something vibration. What is the ring doing? Anybody want the consolation?
My guess is stretching.
Yeah, it's stretching, but this is actually called the ring breathing vibration.
Whoa.
So it's kind of like a lung, and so it's opening up like that. Benzene also has a ring breathing vibration. All of the carbon-carbon bonds stretch at the same time, so it gets bigger, smaller, and like that. So one nice thing about spectroscopy is if you discover some, yeah, we've got a breathing, very good. That's a Chet answer. One of the nice things about spectroscopy is that when you look at new molecular vibrations, at times you can give it names. So we look at some multiple ring systems, and we have ring flapping vibrations. Others called similar vibrations butterfly vibrations. But you can have a lot of fun with names. Okay, you can see this is another carbon-carbon bond stretching vibration, but it's not quite as breathing as the other one was, because this carbon is moving inward, where in the other one they were all moving out, I think. Here's a carbon-oxygen wagging, just like we had in formaldehyde, so that the little dog here with its red tail is wagging it back and forth. And turns out we label these A and B. There are two vibrations that occur almost exactly at the same frequency. This is a combination of rocking of these CH2 groups and some twisting about this carbon-carbon double bond. This is, again, those same two vibrations combining with each other. There's a lot of twisting about this bond. If you take a carbon-carbon-carbon-carbon angle, dihedral angle, that's what's changing. And the lowest vibration is called a ring puckering vibration. It's kind of hard to tell it here, but these middle two carbon atoms go up while all three of the other carbons go down. So it kind of looks like the ring being puckered into lips and stuff. Okay, so should be able to get out of that. I may have to exit screen again. And we're back. And we have to screen share. And we're here. Okay, so what we just looked at were all of these vibrations right here. You see we've listed them all. And did I only come up with 30 vibrations? I must have miscounted. I think I told you there were 33 vibrations, but I guess it's only 30. Okay, so anyway, these are the actual observed frequencies. And what I want you to note is all these first vibrations are very symmetric. And when you have a symmetric vibration, like the ring breathing that we talked about, that would have been this 773 right here. You get the largest change in the shape of the molecule, so these tend to be strong bands in the Raman. And notice they're labeled 1 through 10. If we go to the spectrum up here, you'll see we see vibrations 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of those vibrations we see in Raman spectrum. If we try to look at them in infrared, we don't see 1 and 2. We do see 3 because that was the strong carbon-oxygen stretching. 4 was the carbon-carbon double bond stretch, but it's very weak. And then we see 9 and 10 as little blips. But most of these other bands that we see in the Raman, we don't see. Now, on the other hand, if you look at the Raman spectrum, there are not many bands that we see outside of those first 10. We see 26, 10, 24, 15, 29, and so on. And so there are combinations of bands from this B1 and B2 groups here. A2 bands are strictly forbidden, and if we applied symmetry rules, we would be able to know that. And they're also very often weak in infrared spectra. And so you'll see a couple of these numbers are in parentheses, which kind of means that they're intelligent guesses. Or in the case where we have an L or an S, it means we were able to see it in a liquid or in a solid. Otherwise, all these bands are to the vapor phase spectra of the same molecule. I say we've run out of time, but what I encourage you to do is go to this page, and this is a vector description of what these vibrations are. So carbon-hydrogen stretching at the double bond, symmetric stretching. This one is a symmetric stretching in phase. So just think of these vectors going out, but then 10 to the minus 14 seconds later, they're going to be coming back in. So look at that page. We'll look at it again some more on Monday. I have a chat question. Is problem set 5 still due on Friday the 26th? Yes. And does it include exam 2 material? Yes. So again, no class tomorrow, of course. On Monday, we will continue talking about vibrations of polyatomics. And that, what we get through on Monday will still be on the second exam. Next Wednesday will be a review for the second exam. Then a week from tomorrow, Friday, I will show you nice pictures of melting glaciers and what might happen to Florida and Manhattan if we keep on having global warming. So Friday, I think, should be a fun lecture. There won't be any new material that would be on the second examination. Okay, I will see you Monday then. So have a good weekend. Enjoy your big, long spring break. Stay healthy. There's a question if there'll be a quiz next Friday. I can't answer that. There will not be an hour exam.